Alright, stat students, so we're picking up where we left off the last video. We're comparing the two populations, two samples. So we're going to work another sheet as well with this and just continue going till we get through all this content and continue. Alright, so in the last video, we worked through this worksheet here. We had talked about making a confidence interval. I realized that I actually didn't write down notes for the confidence interval. So for confidence intervals in your notes, these are the requirements. So we have these conditions for constructing confidence intervals about a difference in proportions. So let's write this in our notes. First thing, it has to be random. It's the same concepts that we've been working with all year, as far as these ideas. Like these themes have always stayed here. So that's what we did, and I'll pause this in a second, let you write it. But that's what we did inside of this example here. We saw that it was random, separate random samples. Each one was normal, so we had to check the normality conditions with this large counts here, and then also we had confirmed that they were independent, so that's that 10% condition. So that's what we had done. And then so I'm going to go ahead and pause this, and then we'll put up the confidence interval construction that we did. So I'll pause, let you write this. Okay, so when we were finding our standard error, which here's our formula for the value. So we found Z star, the critical value, the same way we always had. Okay, so this is when the conditions are met. Here's the confidence interval for those proportions. So that's what we had found on here. So we found the critical value, and we had that in the last video with our formula sheet, the different proportions, and then we had our standard error here, and we got these values. Okay, so this will be our formula for the confidence interval, and I think we do have that, I'm pretty sure, in our formula sheet. Let me pull that up. Yes, so this is the confidence interval formula. We've always had that on there. It's the statistic plus or minus the critical value times the standard error. So it tells us here's how you get your statistic, the two populations with proportions. Here's that standard error. This is what it was in chapter 7, and really all the chapters we've been dealing with. That's the standard error. I guess it's here. Yeah, this one here. This is the one here. So we've got that and our statistics. So that's how we're finding those. Now, the next thing we want to do is we want to run a significance test for difference. So we're going to be looking at the next worksheet here, the next sheet here. Okay, so we're going to be running hypothesis tests to compare two proportions. So if you want to draw a line in your note and say hypothesis testing to compare two proportions. So we're going to be running a significance test to compare these proportions. So are teenagers going deaf? In a study of 3,000 randomly selected teenagers in 1988 to 1994, 15% showed some hearing loss. In a similar study of 1,800 teenagers in 2005-2006, 19.5% showed some hearing loss. Does this data give convincing evidence that the proportion of all teens with hearing loss has increased? Okay, so what we want to do is we want to show that the difference has gone up, and with this we always want to start with our hypotheses. We want to state what it is we want to know. So I've got mine already pre-typed out here. So here is the sort of this step. We're going to state the hypotheses, right? We'll test HO. So here, the first one is saying, okay, there's no difference at all. The difference would be 0, so no change. And then alternate is saying, okay, we want to show that the loss has increased. So this difference has increased, okay? at the 0.05 significance level, where P1 is the proportion of teenagers hearing loss 2005-2006, so that's the newer one, and the other proportion is hearing loss in the 80s to the 90s there, so that's the older one. So we're trying to see if there is a major difference. All right, so in order for us to be able to do this, we have these conditions that have to be met. It's the same ones, we just wrote them down, so we're going to check the conditions. Okay, so we can just put that. I'm not going to make you write those again. So we're checking the conditions. So also, what type of test are we going to be doing here? We have a z-test or we have a t-test. So that's the next part. We have the plan. So what is the plan? Well, we are going to use a 2-sample z-test for P1 minus P2 if the conditions are satisfied. So are they random? Are these samples random? Yes, the data comes from independent random samples. Both of them are independent. So randomly selected teenagers, it says in a similar study, so we assume it's random as well. That condition's met. Okay, is it normal? So we check the large counts condition. There's that right there. When you do the multipliers, yeah, they're sufficiently large. Okay, the sample's large enough to make it normal, approximately normal. Then we're looking at the 10% rule. Our population is really all teenagers. So look at that. 10% is 1,800, 10% of all teenagers. Well, no, it's not even close. Same thing with 3,000. So there's plenty of teenagers to go around. In our sample, we said it's sufficiently large to be normal, but it's not too large to where it's not independent anymore. Okay. All right. So we've got that. Now, what we want to do next is we need to find our z-score, right? That's the next part, is the finding the critical, or not the critical value, but the z-score to see if it is significant or not. We got to find that p-value. So we're going to introduce a new symbol here, which is the combined pooled sample proportion. The pooled sample proportion is what it's called. So on our formula sheet, we see this right here. So we're going to be using this formula in to get this critical value. That's what we're going to need. Our test statistic, which is here, is still the same. Okay, it's statistic minus parameter over the standard error. And the statistic is going to be this right here. Okay, then we have the parameter. Well, the parameter is 0, right? That's what we're trying to show, that it's 0 is our null hypothesis. Okay, that's what's going to go on top. Now on the bottom, the standard error, we're used to that being like this, but when we're doing these hypothesis tests, we have this new formula that gets introduced. So it says, so we have this here. We've already written, I said, okay, this is what's going to go here for our statistic minus parameter. Now the standard deviation of the statistic is going to change a little bit, okay? It says if P1 equals P2 is true, the two parameters are the same, we call their common value P. We need a way to estimate P so that it makes sense to combine the data from the two samples. So we have this formula here, x1 plus x2 over n1 plus n2. So that's going to get us P of C. And now we're going to use this formula right here in combination with this one. So we have this right here that goes on the bottom. Now it's a little bit different than what we used on the other tests that we've been using, or excuse me, on the one that's on the formula sheet. Sorry, I lost my mind. This one looks a little different. They just distributed this one here into the parentheses and it went on top. So that's why those look a little bit different. It's sort of, they factored it out, if you will. Okay. All right, so let's go ahead and see how this works. So first thing that we're going to do is we need to find this p hat sub c. That's what we want to do. So let's pull up this and let's go ahead and if we are going to find this, we have, so here is the p p hat of the first one. No, sorry, that is, go ahead and pull up our formula sheet again. That is x1 over x2. I realized my camera was in the way. So this is the count of successes in both samples, and we combine those, okay? So when we look at that, how many successes did we have? Well, if we took 3,000 and 15% of them showed hearing loss, so we take 3,000 times 0.15, 150. So that's where that number comes from. And then 1,800 times 0.195, that's that 351. So that's where we're getting that. And then of course, N is the sample sizes for each. So we get that, and that's going to equal 0.167. Okay, so that's that P hat sub prime. So now we're ready to find our critical value. Okay, so we're using this formula here. Find this, or really it's this one. There's a lot of calculation that goes in. We put that P hat sub C, that's the number we just calculated. That's what is right there. 0.167 is going to go there for all these P hat sub C's. And you could easily type this inside of your Inspire. I think we have enough experience now to do that. But this is what is going to go in there right there. So if you need to take a moment, pause the video to write that down, you can. But we get 4.05. Now that is a huge Z, right? That is a very large Z score. That's going to be pretty significant there. The change, okay, that's several Z scores above. All right. So we remember with these, we have to go on here and we have to find. We go to our table, and this is when we're talking about these tests, we're trying to show greater than, right here. So it's right-tailed. That's what our null hypothesis was. So the right, because it's a greater than what we had right here. It's greater than 0. So it's right-tailed. So we're looking to the right. And that means that as I read this formula sheet, these only show left. So we're looking for the area to the right. So we go here. Largest Z-score we have is 3.4. You look here. If I did, so this is to the area to the left here, 0.9998. So we can imagine that if we do 1 minus 0.9998, we get 0.0002. And we know that this value is further down here than that. Okay, let me actually take a screenshot. So 3.4 gives us this. So the area to the right would be 0.002. But we are all the way here at 4.05. 4.05. So that p-value is even smaller. Okay, even smaller. This is approximately 1, which means the p-value is approximately 0. Okay, because it's going to, again, this is the area to the left. How we have to think of these tables. This is to the left. The right would be 0.002. So we're going to say that this p-value is approximately 0. Okay. So how the statement goes, if the p-value is low, reject HO, right? That's how it goes. So we are going to reject the fact that this has stayed the same, right? There seems to be some evidence that suggests that the mean hearing loss has increased. So we're going to do a conclusion. Okay, we're going to do this conclusion. We'll write this out now. An AP test, that's definitely what you want to do. So since the p-value is less than 0.05, we reject HO. We have convincing evidence that the proportion of all teams with hearing loss has increased from 1988 and 1994 to 2005, 2006. Okay, that's what that's saying. Okay. All right. It says between the two studies, Apple introduced the iPod. If the results of the test are significant, can we blame iPods for the increased hearing loss in teenagers? Well, since we didn't really run an experiment, so this is going back to our to like the very first chapter, and this is good review for that. We can't show causation unless we run an experiment. This is just an observational study here. Okay, so here is the best explanation for this. So for this one, between the two studies, Apple introduced the iPod. If the results of the test are statistically blame iPods. No, since we didn't do an experiment where we randomly assigned some teams to listen to iPods and other teens to avoid listening to iPods, we cannot conclude that iPods are the cause. It is possible that teens who listen to iPads also like to listen to music in their cars. Perhaps stereos are causing hearing loss. And that's what we call confounding, right? So there could be other things causing this. So we want to keep those in mind as we're gearing up for this AP test. Everything is comprehensive. We're having to remember all these details about causation and things like that. Okay. We're not going to worry about this cash for quitters example. That's actually going to do it for this lesson. We'll go ahead and stop there, and I'll be putting up another lesson soon for this.